Welcome to class of Satellite and Radar System. This is Unit 3, Part 4, and we'll be talking about Global Positioning System today, that is GPS. What is GPS? GPS is a satellite-based radio navigation system. It was originally called as Snapstar, which was an operation initiated by United States government. Now also it is maintained by United States government, and it is the first global navigation satellite system GNSS that provides geolocation and time information to GPS receiver whosoever possesses it anywhere or near the earth. So GPS facility is provided by US government free of cost to anyone who possesses a GPS receiver. So we don't have to transmit anything, we can just simply receive GPS signals independent of internet or any other thing. Although internet and all those facilities makes this task makes this whole technology a lot more precise and better. So as US is controlling all these activities, they have all the rights to withdraw the facility. So every country these days is starting with their own navigation system. With India not behind the league, we have also started IRNSS, that is Indian Regional National Satellite System. With its first launch in 2013 and till now, till 2018, we have launched 19 satellites into space. If we specifically talk about Navstar GPS, it has constellation of 24 satellites which are specifically placed in medium Earth orbit. Right. So let's go into detail of this. I always keep a slide blank so that I can draw in few things here. So it is a worldwide radio navigation system formed from a constellation of 24 satellites, and these are placed in medium Earth orbit. MEO is specifically chosen as it is not very close to Earth, so it has better coverage. It is not very far to Earth like GEO, so it has better picture quality, right? So it uses satellites as reference point to calculate positions accurate to a matter of meters, that is advanced form of GPS can achieve centimeter accuracy. So GPS receivers miniaturized, and these are becoming economical and accessible to end user day by day. So the smallest GPS receiver that we own these days could be a smartwatch, could be a watch. So this is the smallest GPS device I am holding with me right now, right? This has its application in cars, boats, planes, and construction equipments, movie making gear, and from machinery, etc. Right? So if we talk about the name, originally it was called as Snapstar. It was manufactured by Rockwell International, a US government initiation. Altitude is mentioned here. It weighs around this size, an orbital period, the plane, 55 degrees to equatorial plane, that is the angle of inclination. Satellite once launched stays up to 7.5 years in the orbit. It has current constellation of around 24 Block 2 production satellites till now, right? So it has mainly got ground segment and space segment. So if we talk about the ground control station, this is also called as control segment. It monitors the GPS satellite, checking both their operational health and their exact position in the space. So we do have a master ground station which is used to transmit corrections for the satellite's ephemeris. So other than providing the location every moment, it keeps on sending the corrections as well, right? So the satellites can then incorporate these updates in the signals as they send to the GPS receivers. There are 5 monitor stations, that is, one is located in Hawaii, Ascension Island, Diego Garcia, and so we have 5 monitoring stations for GPS worldwide. So on the technology or on the principle on which it works is basically called as triangulation, or it is also called as trilateration method. It uses some mathematics to actually calculate the exact position. We know this basically GPS was developed for military purposes in 1973 by American government, US government, United States government. But in 1980s, it was made public, that is freely available to civilians, right? After a plane crash in Korea, so US started providing its services free of cost to other countries. So, but the question is, how does constellation of 24 satellite calculates the location of an object accurately and precisely? For civilian purposes, the accuracy is approximately 10 to 15 meters, which is so accurate. Collecting pictures from such height and using time calculation, how does it makes it possible? So there is some mathematics involved in it, which is called as triangulation or trilateration method. To triangulate a GPS receiver, it measures distance using the travel time of radio signal. We know that radio signal, they do travel with velocity of light. So when we know the velocity and using other parameters, we can actually calculate the distance. How we narrow down that coverage area, we'll see in the preceding slides. So to measure the travel time, GPS needs very accurate timing. So we use atomic clock for this. Timing is critical here. We cannot compromise with even a millisecond of time error. So highly precise and expensive atomic clocks are used. Although providing my every GPS receiver with atomic clock will make the receiver very expensive. Although GPS, one of the good feature of a GPS receiver is these are inexpensive. So what we do, that accuracy can be done with the help of some extra satellite. That is all calculation we'll see, right? Along with distance, the receiver needs to know how exactly where the satellite are in space, right? Finally, the receiver must correct for any delays the signal experiences as it travels through the atmosphere, right? If we talk about the triangulation method, how it works, in triangulation or trilateration method, there are three satellites which are used to calculate the location of an object precisely. See, this is Earth's surface and these are the three satellites which is used to locate this object, how it works. Now for this we have to consider an example, because this is difficult to have the knowledge of distance from three satellites how the knowledge of distance from three satellites allow the position determination. Let's see. Suppose we measure our distance from a satellite and find it to be 11,000 miles. Suppose this satellite calculates this object from its location and it happens to be 11,000 miles, then we do have to draw a circumference with this as the diameter, with this as the radius. We try to draw a circle and the object is supposed to be lying in that covered area. Knowing that we have 11,000 miles from a particular satellite, it narrows down all possible locations we could be in the whole universe to the surface of a sphere that is centered on the satellite. So from the satellite of this much distance, we take this as radius and try to draw a circle. So it narrows down the location, it narrows down the possibilities with that sphere, right? Now from another satellite, if we calculate the linear distance and it happens to be 12,000 miles. Now again we are going to draw a sphere or a circle on Earth's surface with that distance. An intersection of the previous circle and this circle, that will be the location, that will be the point where object could be lying. That will be the complete region where object could be lying. This is the interference, that is intersection region. That tells us that we are not only on the first sphere, but we are also on the sphere that is 12,000 miles from the second satellite, or in other words, we are somewhere on the circle where these two spheres intersect. So we have narrowed down the location from complete Earth to a intersection region, right? Now then if we make a measurement from the third satellite and suppose it happens to be 13,000 miles, then we again draw a circle using this dimension, and now we have the common area of these three circle intersection, right? That narrows our position down to even farther to the 2 points, these 2 points where all three lines intersect. So my object could be lying here or here. cuts through that circle. That's the intersection of the first two spheres, right? So this is how we narrow down. Now the question is, if that is the distance, how this is how we calculate the position. First thing, that is the position. So, and this is 10 to 15 meters approximate, right? So with the help of, ideally with the help of 3 satellites, we do all this calculation. Now the question is how measuring the distance from satellite is made easier. Now the thing is, we know that radio waves, they do travel with the velocity of light, and velocity of light is 3 into 10 to the power 8 meters per second, right? So the distance could be calculated as velocity into time, which is taken by the signal to travel, right? So from the last section, position is calculated from the distance measurements to at least 3 satellites. But now the question is how to measure the distance. So as we know, radio waves, they do travel with this velocity. We can calculate the distance by knowing the time at which the signal was transmitted and is received back, right? So we know the time of travel, right? Although this time of travel will be the double of the distance, right? So measuring time travel even requires some codes, and these are the pseudorandom code, PRC code, which are transmitted by each satellite. This makes our communication secure, right? Physically, it is a pseudorandom sequence. We know that nothing is random in this world, so this is a pseudorandom sequence. So we do have pseudorandom sequence generators, which send sequence of on and off pulses. Now receiver knows the time of transition of the satellite sequence. Now by synchronizing the received sequence with a locally generated sequence, the receiver can identify the relative delay between the satellite and its location. Suppose it was transmitted here, but it was received like this with this much of delay. We can see the sequence, this sequence starting here. So this much is the delay which was observed. So this is the time elapsed between 2 satellites and the receiver. So this is the time which is used for calculation. It was transmitted here, but it is received here. So this time gap will give me the time elapsed, right? So we do have the time information, we know the velocity, we can calculate the distance. So this is what is applied basically. So this is seems to be a simple calculation, but it requires a lot of precision and error correction. So reasons for using pseudorandom sequences: it avoids accidental synchronism with other interfering signals. The patterns are so complex that it's highly unlikely that a stray signal will have exactly the same shape. So using pseudorandom sequence has its own advantages. Since each satellite has its own unique pseudorandom code, it will allow satellite identification, that which code is transmitted by which satellite, as each satellite will be having its own code. So all satellites can use the same frequency as they are using different code. So we are reusing the frequency, right, which is a very good advantage, achievement in case of communication, reutilizing the bandwidth. Pseudorandom sequences, they also make it more difficult for a hostile force to jam it. So it is used for security purposes as well. And most importantly, the spread spectrum effect gives a spreading gain, which allows receiver to amplify the signal, right? As signal is traveling such long distance, but by using this spread spectrum effect, the gain can help us amplify the signal and the signal at despreading, which is a very good advantage. Now, if we talk about GPS signals, what are the various signals that we specifically use for GPS? We use L1 carrier and L2 carrier. L1 carrier is 1575.42 megahertz, and it carries both the message and the pseudorandom code for timing, whereas L2 carrier is 12,227.6 megahertz, and it is used for more precise military pseudorandom code, right? So for civil and military, we do use two different frequencies just to keep our military communication separate from all other sort of communication. So navigation message at low frequency, signal added to L1 codes. L1 codes that gives information about the satellite orbits, their clock corrections and other status. Right? Now if we talk about what are various kind of codes that we use for GPS system, there are two different kind of codes, right? Coarse acquisition and precise code. So keeping in mind military communication and civil communication, we use different kinds of code for each of the application. The coarse acquisition CA code is used with the help of L1 carrier. It modulates the L1 carrier which is 1575.42 megahertz. It modulates this carrier and it repeats every 1023 bits and modulates at 1 megahertz. Each satellite has a unique pseudorandom code and this is basically used for civilian purpose. Data rate is 1.024 Mbps. For military purposes, we basically use precise code, which is also called as P code. It repeats on a 7-day cycle. We keep on changing it. And it is capable of modulating both L1 and L2 carrier at 10 megahertz rate. This code is intended for military users and the main advantage of it is it can be encrypted. So military communication has to be secure all the time. So we use cryptography, that is encryption schemes on it. We do have linear block codes, different kind of coding schemes which are applicable here. When it is encrypted, after encryption, my P code is called as Y code. So P code after encryption, it is called as Y code, encrypted version. Data rate is high here, we can see, right? So if we talk about measuring distance, then distance to a satellite is determined by measuring how long a radio signal takes to reach the user from the satellite, right? Now to make the measurements, we assume that both the satellite and the user's receiver are generating the same pseudorandom code, right? At exactly the same time. Now by comparing how late the satellite pseudorandom code appears compared to the receiver's code, the receiver determines how long the signal took to reach, right? Transmitter and receiver, they generate at same time, and through the transmitter, when the receiver receives, it knows the time elapsed, the time gap between the two signals. So that time gap is the time taken for the signal to travel that distance, which is denoted by TT. So distance is calculated by speed into time or velocity into time. We know this velocity is velocity of light and time elapsed is calculated, distance is measured. So here in the triangulation method or trilateration method, we take use of 3 satellites, but practically a 4th satellite is also used to compensate for the errors that has occurred, because you know, making every GPS receiver atomic clock enabled is a expensive process. So to instead of that, we use a 4th satellite, an extra satellite for that timing correction. That will study how the calculations are carried out using that 4th satellite in preceding slides or lecture. So let's see here, by comparing how late the satellite's pseudorandom code appears compared to the receiver's code, the receiver determines how long the signal took to reach it. Then multiply that travel time by the speed of light and you have got the distance. This is what I have done here, right? Now if I talk about timing, the third thing, after distance, the third thing is timing calculation. Timing is critical, right? Remember that both the satellite and receiver need to be able to precisely synchronize their clock. Even 1 millisecond of error will cause me a error in kilometers, right? So we cannot compromise with timing errors. So on the satellite side, timing is almost perfect because they have incredibly precise atomic clocks on board. Satellites are expensive thing, they can be boarded with atomic clocks, but receivers are not so accurate. So how these errors are diluted? Like this was the suppose correct calculation, this is incorrect calculation because of the timing error. So with the help of 3 satellites, if this is the correct calculation, with the help of 3 satellites, from correct calculation from here reaches here. So let's use a 4th satellite for this correction of this distance, right? So if our receivers needed atomic clock, this will make it expensive. Solution to this problem is to make an extra satellite measurement, that is with the help of the 4th satellite. This is one of the key elements of GPS, and as an added side benefit, it means that every GPS receiver is essentially an atomic accuracy clock. Although it is not installed in here, but with the help of measurement of that 4th satellite, it is enabled. If 3 satellites can give imperfect calculation, 4th will give perfect calculation, right? 4th imperfect calculation. If 3 perfect measurements can locate a point in 3-dimensional space, then 4 imperfect measurement can do the same thing, right? This is shown from here. If I use 4th satellite also, this error will be minimized to 0. If timing was perfect, then all satellite ranges would intersect at single point, which is the receiver's position. But with imperfect clocks, a 4th measurement done as a cross-check will not intersect the first 3. So it will be at a distance from the first 3 intersection, and that distance will be the error, and that will be removed. So the receiver's computer can detect the discrepancy in time measurements and recognize how much we have to undo the error. Since any offset from universal time will affect all of the receiver's measurement, the receiver looks for a single correction factor that can subtract from all the timing measurements that would cause them all to intersect at a single point. That correction brings receiver's clock back into sync with the universal timing, providing atomic accuracy to it, right? So that's it for today. This is how GPS works. We have spoken about distance and timing calculation and timing accuracy and synchronism need. Thank you, and these are the references which I have used.